All right, math magicians, on this great day, we're going to be using patterns to factor special polynomials. The nice thing about this is that if you do memorize the pattern, woohoo, everything's going to be so much faster, like super faster. However, if you don't memorize it, you can always use Snowflake. You can always use Snowflake for these. So today we're going to show you how to do it fast. I encourage you to do it fast, but worst case scenario, you can always use Snowflake. So looking at the first one here, I put negative 54 on the top, I put negative 3 on the bottom, x is in the wings, and negative 9 plus 6. So now we get the x minus 9 and the x plus 6 as my factors. When we factor out this one, of course, we get x minus 6 quantity squared. When we factor this one, we get a minus 6 and then a plus 6. If you recall, those have a special name. Good, so these things are called conjugates. They're not opposites, they're conjugates, just because the middle component are, the middle operation is different. And sorry, that's not a B, I need to correct that. It's, got to check to make sure my handwriting is legitimate. That's a 6. All right, and then as we did this one, B plus a 7, and we quantity square that one too. Okay, again, notice the pattern that we are establishing here, that these factors are factors of 54, but they add to the negative 3. Well, it turns out here, notice this, a same thing happens. Negative 6 times negative 6 is positive 36. But when you multiply and double, you get negative 12, or just the double of those two. Negative 6 doubles to negative 12. Over here, 7 doubles to 14. And when you square it, you get 49. So what we're going to do is show you that there is a pattern that results when we have what's called a perfect square here. That's a perfect square, as is this. And over here, we have conjugates. So let's walk through the rules, see what we get. So our super secret rules. These are our super secret rules for factoring special polynomials really fast. And that's the official name for it in my class. The difference of squares. Difference of squares. The difference of squares become conjugates. The difference of squares becomes conjugates. So, watch the magic here. If you have an a squared minus a b squared, that just instantly, you have an a and a b, and one of them is plus and one of them is minus. That's it. These guys here, they have to be perfect squares. Perfect squares. Then all we do is square root them and make 1 plus 1 minus. So look down below. I look here. Oh, this is a difference of 2 squares. It's a difference of 2 squares. Great. So square root that to get a 6. Square root that to get an x. Make 1 plus, make 1 minus, and we're done. Now we could have done Snowflake as well to do this, but it's slightly more complicated with this, so I won't do it now. But there we go. You recognize a difference of 2 squares, so you square root, make 1 plus, 1 minus. And it never matters which one's plus and which one's minus. All right, the next one. This is odd because in the way I'm teaching it, we have the word probably, which is rarely the case in math until we get to probability. A trinomial with perfect squares on the ends. Look, a perfect square here and a perfect square here. Perfect square here and a perfect square here. On the ends, and actually I'll put S there, ends, will probably become a square of a binomial. The reason why I put the probably is because you have to do a test at the end, the way I'm teaching it. Okay, so it actually is very quick. You have an A that's being squared, minus 2ab plus b squared. So all we do is a This symbol here is a minus, so we put a minus. And this b right there is a b. All of it is squared. And the exact same thing applies for down here, where I am going to say a, but this time it's a plus b quantity squared. When I say quantity squared, I mean the end parenthesis. So what's the thought process here? The thought process is, oh look, perfect square and a perfect square. So if I square root this, I get an n. If I square root this, I get a 5. And I bring down this symbol right here to be a plus. And that's it. Now I put parentheses and square around it. To test it, to make sure I'm right, I have to multiply these to get it 5n and double it to get 10n, which you see here is the same. All right, so let's walk through. First off, when in doubt, work it out. You can use a snowflake. You don't have to memorize it, but I highly encourage you to. It speeds up a lot of things. So let's take a gander here. Example C. What is the factored form of the following here? The following here. So notice what I see here. Perfect square and a perfect square. And this is the trinomial one. It's a trinomial. So because of that, I'm going to be using one of these rules. So that means it's going to end up being a perfect square like this. So bring down the x, bring down the 7, and bring down the plus. And we're done. Going to test it real quick. 7x doubled is 14x. 7x doubled is 14x. So now I can commit to the answer. Oh, Swenson, that's too confusing to me. Okay. It's okay if you're confused. I encourage you to just work slowly, step by step through it. But you could always just do 49 and 14, put x's in the wings and 7's here, and notice x plus 7, x plus 7. Okay? It'll still work. Notice, though, that my method is a little bit faster than the snowflake. Now, before you give it another try, let's see what we have here. Notice what we have. A difference of squares. Perfect square there. Perfect square there. So whenever you have a difference of squares, you get conjugates. X, 7's, one of them is plus, one of them is minus. We're done. That's it. Difference of squares will always become conjugates. So checking this one, x minus 4 quantity squared. Double check, double check. Multiply these to get negative 4, double negative 4x, and double it to get negative 8x. So now it's no longer probable, it's exact. This is the answer. This guy here, it's always going to be conjugates. Because I have a difference of two squares, so it's 8's, b's, one's plus and one's minus. Which one's plus, which one's minus? It never matters. Just put them somewhere. All right, making things slightly more complicated here. Instead of having the leading coefficient being only letters, notice I have numbers involved in here as well. So I ask myself here, because I see a trinomial, most likely it's going to end up being a perfect square like this. This is a subtraction, so we bring that subtraction down. But this is what you have to do. You have to take the square root of the whole thing, not just the x squared, but the 9 as well. So bring down the 3x. And over here, you're taking the square root of the 25, which is a 5. I'm just going to test it to make sure. When I multiply these, I get negative 15x. And when I double it, I get negative 30x. So that is a check. Next one, difference of squares. Oh, great. Difference of squares means I'm going to have conjugates. One's plus, one's minus. When you square root this, you get 4x. So I put 4x's there. And when I square root this, I get 11. And I put 11 in both of those. And that's it. Done. Got that. Now, the next thing we're going to do is factor completely. So let's make a quick list over on the side of all our tools when factoring. Our tools when factoring. Okay, the first thing we always are going to check is actually GCF. And we've actually done that in the previous snowflake notes, 9b. Another thing that we're going to check is, are there special factors? Because that we can just do mentally. And then lastly, go ahead and do snowflake there. Now, of course, snowflake will always work if you forget number 2, but you have to do GCF first. You always have to check GCF. If you do not GCF, then the other stuff does not work so well. So always check GCF. So that's what we're going to look at here. Is there a greatest common factor that I can divide each of those terms by? And let's see. Well, at first I'm tempted x's, but this one doesn't have an x. So what number can be factored out, folks?
3.
All right. So if you do snowflake like this, or excuse me, not snowflake, but if you do the ladder method and pull the 3 out, notice I get x squared minus 20x plus 100. And now I notice a perfect square in the front and a perfect square at the end. So bring the 3 down. Now we can square root the x, square root the 100 to be 10, and don't forget to bring down the negative there. And now I'm perfectly factored. I'm just going to double check that the perfect square works out here. If I multiply this, I get negative 10x, and double it to get negative 20x, and that's good to go. So this is my final answer. I factored it completely 3 times x minus 10 squared. Don't forget that whatever you factor out at the beginning has to show up at the very end. We just temporarily ignore it when we snowflake or use our rule. Let's do the next one here, part B. If I were to, I do notice that I have a 3 here and this divided by 3, and I have an x and a y in both of them. So if I gave myself the ladder, and I'm going to get rid of that b just to see what can come out, and I can pull out a 3xy from both of those. Notice that I get an x squared here minus a 4y squared. And so then I notice that this right here is a difference of squares. So I'm going to use the supersecret rule for difference of squares, where I get conjugates. I get x minus 2y and x plus 2y. And don't forget to bring down the 3xy. And there we go. Notice I didn't have to do snowflake. And I didn't even have to bother with that the y squared thing. That's okay. It's a perfect square right there. So I square rooted to get those 2 terms there. So by way of review, here are some supersecret rules to remember. And notice you have to identify first. If I see a trinomial such that we have a perfect square here and a perfect square here, then I'll probably use this one. If I see 2 squares being subtracted, then I'll use this pattern here.